Okay, got a pendulum, mass 0.4 kilograms, 180 centimeter length, release from rest at T equals 0 from position at negative 180 centimeters, right? We could draw a picture, and you should, but I'm going to skip that for the moment because you know what it looks like, okay? So what's the first thing we know?
We can find K.
Well, yeah, before you find K, and that's exactly the first thing you need to do, so that's a good answer. But before we find K, we have to invoke a principle. What's the principle? The principle isn't find K. What principle leads us to want to find K?
Knowing that this is simple harmonic motion.
In what now? I think you said somehow that this thing's going to be in simple harmonic motion. That's not a principle. What is the condition that dictates simple harmonic motion, so we go on and do what Alexander just said, which is the right thing to do first, so it was a good answer. But what's the principle? What do we have to say before we do that if we're going to give a completely grounded solution?
The net force has to equal negative K times your R vector.
Well, we'll go with negative kx right now, but in multivariable calculus terms, that's the way you would want to say it, right? So rather than confusing the thing with that, if we're in one dimension, we can just talk about x, and it can be positive or negative. We don't even have to worry about I and j vectors and stuff, okay? I included them here because sometimes you got to do that, and I want you to do that because that's how I want you to do projectiles in terms of the vectors, okay? But, you know, that's kind of an aside. So you're absolutely right. The principle that a net force, net linear restoring force, implies simple harmonic motion. Okay? About the 0 point of that force. And in this case, the 0 point of that force is taken to be 0. That's our usual solution, but not necessarily always, and we'll see exceptions. Okay, so we have that.
We also know that the kinetic energy is equivalent to the inertia times the, what is it? Yeah.
Well, yeah.
No,
Yeah.
potential energy.
Well, you use what you know about potential and kinetic energy to find the potential energy at a position x, right? So we'll do that in a minute. But your principle is, first of all, this. Okay? Now there are different ways you can formulate your principles, but that's the one I'm kind of recommending that you use. So, x equals a cosine omega t plus phi, right? Now, do we know what omega is? Can we find what omega is? What do we have to do first? Well, we said it, right? Got to find K. And before you can do anything about energy, you got to find K as well. So let's find K. And then we'll apply another principle, energy principle, right? Definition of potential energy, definition of work. Very simple. Very easy integral. Don't even actually need an integral. We'll do the integral. Okay?
Technically, you don't even need to.
Sorry?
Never mind, I was thinking of something.
Okay. Okay. So, well, K. Now, I said something pretty foolish up here, because I say we're releasing at x equals negative 180 centimeters. It's not a whole lot less than the length, is it? Okay? Actually, it is.
I mean, that is also possible.
So I'll just really, I'll pretend I hadn't written that 0 there. That's less foolish, okay? Now it's only 1/10 the length. That's lesser enough that you're not going to have much of an error in omega, okay? Not even, probably 0.1%, but not nearly 1%, okay? So, okay, well, and you don't really even have a constant omega if it's not low amplitude, okay? There's always a little uncertainty due to the fact that your amplitude is still finite and the direction of motion is not exactly horizontal, okay? Again, we don't worry about that in this course, but differential equations we'll play with, okay? Okay, well, so we have this. And now we can easily find K. Now there are details of why K equals this. They go back to the differential equation, and that is something I want you to be able to connect. Okay? So we're not going to derive the differential equation and solve it and do all that. That's a little too much. But you should be able to do it. K equals 0.4 kilograms. And I'm just going to use 10 meters per second squared. Divide that by 1.8 meters, okay? And you get I think those are the right numbers. All I got to do is put the decimal in the right place. Okay? Those numbers right?
Pretty close. It 2 repeating.
Is it? Oh, doggone it. I'm losing it. Okay, well, anyhow, we'll just do this, okay? And I'm just going to say approximately. And I think it's 2.2 because it's 22. No, it's 2.2. It's like 4 divided by 1.8, right? Okay? Not that hard to divide either. I was going by the fact that when you divide by, never mind. When you divide by 9, you get 1.11 repeating. So if I'd have doubled that, I'd have got 2.22, and that's what I should have done. Instead, I did something kind of foolish. Okay. So there's our K, right? So now we can find omega. Now I'm not going to write out how you do this. You can do this, right? It's 2.2 divided by 0.4, which is what? It's 5.5, right? Square root of 5 is about 2.2. Square root of 6.25 is about 2.5. So I'm going to say it's about 2.3 something, but it might be, yeah, I think it's going to be 2.3 radians per second. And there's no way I'm wrong about that. Except maybe I'm wrong. It's 2.3 or 2.4. See why I don't like to use calculators? They take so long.
2.36.
3.6? How could I be off? But, well, yeah, I said I might be.
Well, 2.357.
Yeah, well, it was close. Okay, 2.4 radians per second ballpark. Of course, this isn't going to be precise enough to predict where that pendulum is going to be 3 days later, is it? You need probably 5 significant figures to predict that. Okay. Actually, 3 or 4 days would be actually closer to a significant part of 1 million. Yeah, you'd need 7 significant figures. Okay? Probably not gonna get that. Okay, so, and if, check me out on that. I could be wrong. Top of my head isn't as good as it used to be. Okay, so omega is 2.4 radians per second, ballpark. And now, x equals A, the amplitude. What's the amplitude? Well, if you release it from 18 centimeters and it doesn't lose any energy, it's going to have to swing out to 18 centimeters on this side, 18 centimeters on this side, keep doing that. Now we know it loses energy, the thing we did in lab last time, which is that thing. It was a rotational harmonic motion. Maybe it was a simple harmonic motion, except the amplitude kept decreasing. Okay? So, you multiply that by an exponential and you get the thing. But even that's not a perfect model. Okay, so, x is then going to be I could just write second to the -1 because I don't have to write the radian, but I'm going to remind myself what this means. It's radians per second, right? So I'm going to write it like this. And there we have it, except for phi. What's phi?